everyone, my name is Michaela and today I'll be talking about acid-base equilibrium. Acid-base equilibria are constantly in action in the world around us, whether it be what happens inside us, the interactions between food and drinks we eat and our bodies, or in naturally occurring or human-driven environmental processes. It's important to understand the basics of acids and bases in order to apply it to real-world situations. A knowledge of conjugate acid-base pairs is a good first step in understanding acids and bases. In this example here, ammonia acts as the conjugate base to ammonium ion, and water acts as the conjugate acid to hydroxide. These here are called the conjugate acid-base pairs. I'll now quickly go over a few concepts that scientists tried to use to theorize acid-base behavior. First off is the Arrhenius theory, which focuses on the release of hydrogen or hydroxide ions in acids and bases. This is considered to be an incomplete theory because it assumes that all acids contain hydrogen and all bases contain hydroxide, which isn't the case. Secondly, the Bronsted-Lowry theory is another incomplete theory, however it has some useful parts. The theory states that conjugate acid-base pairs differ by one hydrogen ion, with the acid being a proton donor and the base being the proton acceptor. The theory also states that when dissolved in water, acids will protonate to form a hydronium ion and bases will deprotonate to form a hydroxide ion. Finally, the Lewis acid-base theory focuses on electron transfer. A Lewis acid is called an electrophile, meaning it's the electron pair acceptor, and a Lewis base is considered to be a nucleophile, meaning it is an electron pair donor. The concept of pH is very important in many everyday activities, such as making sure your pool is safe to swim in, or in any other situation. The concept of pH is very important for many everyday activities, such as making sure your pool is safe to swim in, or in any other situation where checking the chemical conditions of a solution is needed. The term pH was first proposed by a Danish biochemist, and it refers to the potential of the hydrogen ion. Looking at the diagram of the pH scale here, acidic solutions have a pH between 0 and 6, neutral solutions have a pH of 7, and alkaline or basic solutions have a pH between 8 and 14. This number is determined by taking the negative logarithm of either the hydronium ion for pH or the hydroxide ion if you're looking for the pOH. The ion product of water, Kw, is given by the product of the concentrations of hydronium and hydroxide ions at equilibrium in the self-ionization of water. At the standard conditions, this value is 1 times 10 to the negative 14. The pKw is given by taking the negative logarithm of the hydronium and hydroxide ion concentrations, and this number should always equal 14. This is the same as saying that taking the pH and pOH must always add to equal 14. For example, if you have a hydronium concentration in a solution of 2.5 times 10 to the negative 3 molar, the pH would be 2.6. Every acid and base has a specific value that describes its strength, which is quantified by its equilibrium constant for the reaction describing its ionization in water. This value is called the ionization constant, Ka for acids and Kb for bases. Ka and Kb span a huge range of values, so it's sometimes easier to work with the pKa or pKb values. These values can be determined by taking the negative logarithm of the ionization constant. Conversely, the Ka value can be found by taking 10 to the negative exponent of pKa or pKb. Strong acids tend to have very large ionization constants, so the K value is much greater than 1. Weak acids and bases tend to have small ionization constants, with the K values much less than 1. In this example, we take a look at the ionization constant, pKa, for hydrogen peroxide. To determine the Ka for this expression, we set it up like any other equilibrium expression, with the products over the reactants. And this should give us a value of 1.8 times 10 to the negative 12, which will always be true. Now to find the pKa, we take the negative logarithm of the Ka value to get a value of 11.74. When Ka or pKa values are exploited, the reaction will shift accordingly towards the products or the reactants to maintain equilibrium. This follows Le Chatelier's principle. Indicators are very commonly used in acid-base chemistry to show changes in pH levels, They display different colors in acidic or basic conditions. So the symbolic representation of indicators is given by the equation HIN in water is in equilibrium with H3O plus and IN negative, where HIN is the acid color and IN negative is the base color. When you increase the hydronium ion concentration, it shifts the equilibrium to the left, which increases the proportion of the acid color. Decreasing the hydronium ion concentration shifts the equilibrium to the right, which increases the proportion of the base color. The overall color of the solution is dependent on what proportions of the acid and base are present. This diagram from the textbook depicts many different acid-base indicators and the pH changes they describe. For example, alizarin yellow changes from yellow to violet and pH ranges from 10 to 12. Methyl red here changes from red to yellow and pHs from 4 to 6. So we've gone over everything we theoretically need to know about acids and bases, so now we can move on to doing a practice problem. Part A of this question asks us to determine the concentrations of the hydronium ion and acetate ion in a 0.3 molar solution of acetic acid. So to start off this problem, we write the balanced dissociation equation for acetic acid in water. Next, we set up an ice table with the only initial concentration being 0.3 molar of acetic acid. We can assume that the value of x will be small enough to approximate to 0 in the 0.3 minus x molar, so we end up with a concentration of 0.3 molar of acetic acid and x amount of hydrogen ion and acetate concentration. Next, we set up the Ka expression, which is our products over the reactants. So we've got the concentration of hydronium ion and acetate over the acetic acid concentration, which will give us x squared over 0.3 molar, which is equal to the Ka expression for acetic acid, which is 1.8 times 10 to the negative 5. Solving for the value of x, we get a final concentration of 2.314 times 10 to the negative 3 molar. So the value of the concentration of hydronium ion and acetate ion at equilibrium will be 2.31 times 10 to the negative 3 molar. Now to find the pH of this solution, we take the negative log of that concentration, which will give us a final pH of 2.64. So for part B of the problem, we'll look at how the ionization of acetic acid is affected by the addition of hydrobromic acid. We'll start off this question similar to the previous one. However, this time the initial concentration of acetic acid is 0.3, as well as the H3O plus concentration. So now our values at equilibrium will be 0.3 minus x for acetic acid, x for acetate, and 0.3 plus x for H3O plus. And again, we're approximating these values just to both be 0.3. So the Ka is equal to the concentrations of the products over the reactants, which gives us 0.3 times x over 0.3. And this is equal to the Ka for acetic acid, which is 1.8 times 10 to the negative 5. As you can see, both 0.3's cancel out, so we have x is equal to 1.8 times 10 to the negative 5. So our final concentration for acetate will be xm, so that'll give us 1.8 times 10 to the negative 5 molar. For the hydronium ion concentration, it's 0.3 plus xm, which will give us 0.3 molar. Comparing the acetate ion concentrations from parts A and B, you can see that the concentration gets significantly lower with the addition of HBr, which means it suppresses the ionization of acetic acid. Acid rain is a classic example of acid-base chemistry in nature. It is caused by nitrogen oxides and sulfur dioxides produced by both natural processes and the combustion of fossil fuels. When these oxides react with oxygen and water in the atmosphere, nitric acid and sulfuric acid are produced. While the effects of acid rain can be concerning, rain should be naturally slightly acidic, produced by the natural reaction of carbon dioxide and water, which eventually produces carbonic acid, giving rain a pH of around 5.6. However, the average acidity of rainwater has increased at a higher than normal rate over the years with the burning of fossil fuels, and now has a pH of around 4 to 4.5, and can get even as low as a pH of 2 in some places. On the screen here you can see some of the chemical reactions involved in the increase of rain acidity. Scientists and researchers have made progress in decreasing the effects that worsen acid rain. Most coal-burning power plants now use scrubbers, which essentially trap sulfur dioxides from being released into the atmosphere. Research has also been done in the desulfurization of fossil fuels, making their combustion cause less of a harmful impact to the environment. Thank you so much for your attention in my presentation. I hope you learned something new about acid-base equilibrium.